Welcome to Chapter 3, Python Environment and Data Preparation. Here we build the practical skills for setting up Python and getting messy data ready for machine learning. There is a saying among practitioners that machine learning is 80% data wrangling and 20% modeling, and most days the 80 feels generous. This chapter is where you build the muscles for that work. By the end of this chapter, you should be able to explain why Python is the default language for machine learning, set up a working environment, use Jupyter Notebook, describe the core libraries, and load and inspect a dataset with pandas. You should also be able to detect missing values, duplicates, and suspicious entries, clean data by filling or dropping them, and encode categorical variables into numerical form. Figure 3.1 shows a typical data preprocessing pipeline. The key rule is that every step must be fitted on the training data only, then applied to the test data, so no information leaks from test back into train. Why is Python the language of machine learning? Walk into almost any data science team and you will find Python on every screen. A small set of libraries does most of the heavy lifting. NumPy handles fast numerical arrays. Pandas manages tabular data. Matplotlib draws plots. Scikit-learn provides classical models and tools. And Jupyter Notebook ties it together for interactive work. Setting up your environment comes first. A Python environment is simply the bundle of tools, packages, and settings that your code runs inside. One easy option is Anaconda, a free Python distribution built specifically for data science, with the common libraries already included. Another option is Google Colab, which runs notebooks in the cloud, right in your browser with nothing to install. Jupyter Notebook is where most experimentation happens. A notebook is built from code cells, which run Python and show output beneath, and markdown cells for notes. A good habit is to narrate as you go, with a short note before each code cell. Let us start with NumPy, the foundation almost everything else stands on. This short snippet creates a NumPy array of numbers and then computes its mean and multiplies every element, showing how compact array operations can be. Notice that multiplying the array by 2 scales every element at once with no loop in sight. That vectorized style is what makes NumPy both fast and concise. Next comes pandas. If NumPy gives you fast arrays, pandas gives you the spreadsheet. Here we build a small data frame with a name and an age column, then preview it. A data frame is essentially a table with labeled columns and rows. 3 commands earn a place in your muscle memory. Head shows the first few rows, info reports, column names, types, and non-missing counts, and describe prints summary statistics for the numeric columns. Now let us load real data. Most data sets you meet live in CSV files, and loading one is a single line. This code loads the Titanic dataset straight from Seaborn with no file needed, then reports its shape, previews the first rows, and prints column information. Before touching a model, give any new dataset a thorough once-over. How many rows and columns? What does each column mean? Where are the missing values? What are the data types? And are there impossible values, like a negative age or a fair of 0? A quick way to count missing values per column is worth memorizing. This single line sums the missing entries in each column, giving you an instant map of where the holes are. Run it and the trouble spots jump out. Age is missing for roughly a fifth of passengers, embarked is missing for a couple, and deck is missing for the large majority. So how do we handle those gaps? Real data has holes, and pretending otherwise only pushes the problem downstream. One approach is to remove rows or columns. If only a handful of rows have a missing value, dropping them is harmless. Here we drop the deck column, which is too sparse to be useful, and drop the 2 rows that are missing the embarked value. For a numeric column with scattered gaps, like age, filling, or imputing, the holes lets you keep all your rows intact. This snippet computes the median age and uses it to fill in every missing age value. The median is a robust choice because it resists the pull of extreme values. For a categorical column, you can fill gaps with the most common category or with an explicit unknown label when not knowing is itself useful information. Here we find the most common embarkation port using the mode, then use it to fill the missing embarked values. There is no universally correct choice here. The right field depends on the column and on what the missing value really means. Next, we tackle duplicates and outliers. Duplicate rows quietly distort everything downstream because they let some examples vote twice. This code first counts how many duplicate rows exist, then removes them so each example is represented only once. Now we turn to encoding. Most models speak only numbers, yet much of the Titanic data is text. Sex is male or female, and embarked is a port code. The simplest approach is label encoding, which maps each category to an integer. Label encoding suits ordered categories, where saying 0 is less than 1 is less than 2 actually means something. The catch with label encoding is that it invents an order even when none exists, so for unordered categories, we reach for one-hot encoding instead. This code one-hot encodes the sex and embarked columns, turning each category into its own indicator column. The drop first option removes one redundant column per variable. This keeps the encoding compact and avoids a subtle redundancy that can trip up linear models. Even after encoding, one issue remains. Numeric features often live on wildly different scales. One remedy is standardization, which rescales a feature to have mean 0 and standard deviation 1 by subtracting the column mean and dividing by its standard deviation. This code uses scikit-learn's standard scaler to standardize the age and fair columns together in a single step. The alternative is normalization, which squeezes each feature into a fixed range, commonly 0 to 1, using the min-max scaler. It helps to watch the whole cleaning arc happen on a table small enough to check by hand. Here are 6 customers before cleaning. One age is missing, shown as a question mark. City is an unordered category, and the monthly fee sits on a much larger scale than age. Working through the numbers, a fee of 120 standardizes to about minus 0.82. Doing the same for every age and every fee produces a fully numeric table that a model can finally read. Here are the same 6 customers after cleaning. The missing age imputed, the city one hot encoded with Lisbon as the dropped baseline, and age and fee standardized. Every value is now numeric. Doing these steps by hand, one cell at a time, is fine while you are learning, but there is a cleaner way to organize them. A machine learning pipeline chains the steps in order: handle missing values, encode categorical variables, scale numerical variables, and finally train the model. Because the whole sequence is one object, calling fit on the training data and predict on new data applies every step automatically and in the right order. Here is the key point. Never fit a scalar, imputer, or any pre-processing step on the full dataset. Fit on the training set only, then apply the learned parameters to the test set. Fitting on everything leaks test information and gives a falsely optimistic score. Stepping back, the entire pre-processing workflow you have just practiced follows a stable arc. That arc has 8 stages: load the dataset, inspect it, identify the target you want to predict, handle missing values, encode categories, scale numbers, split into training and test sets, and finally train and evaluate a model. The next figure lays out this data preparation arc as a vertical pipeline, from loading the raw file to the train test split that hands clean features to the model. Figure 3.2 shows that pipeline in full, flowing from loading raw data through cleaning and encoding to the train test split that feeds the model. That final split deserves a closer look because it is what keeps an honest score honest. Figure 3.3 shows a typical 3-way split. The model learns only from the training set, the validation set guides hyperparameter choices, and the test set stays untouched until a single final evaluation. Now let us tie the chapter together. The snippet ahead loads the Titanic data, cleans it, encodes the categories, and trains a first model to predict survival. This longer example walks through the full arc. It loads the data, keeps a clear set of columns with survived as the target, fills missing values, one-hot encodes the categories, and then separates the features from the target. Pay attention to the order of operations in the splitting and scaling steps because doing them in the wrong order is exactly how test information leaks in. Let us close with a case study. A subscription software company wants to predict which customers will cancel, but its data is scattered across billing, support tickets, and usage logs. Merging and cleaning all of it is where most of the project's effort goes. The raw export is exactly the kind of mess this chapter prepares you for, and working through it follows the now familiar arc. The lesson the whole chapter has built toward is simple. The algorithm is the easy part. Let us see it in code. The following program simulates the messy customer data set, applies the full pre-processing arc, and trains a logistic regression model to predict churn. This code generates 500 synthetic customers with realistic quirks, such as inconsistent casing in the plantier, then standardizes those labels to lowercase and encodes the categorical column before modeling. Because the target here is just random noise, accuracy hovers near 50%, which is the expected baseline. On real customer data with genuine signal, the accuracy would rise substantially. To summarize, Python became the default language for machine learning thanks to its readable syntax and rich interoperable ecosystem. And scikit-learn's pipeline bundles the cleaning steps into one object that applies them consistently every time. If you want to go further, explore the documentation for scikit-learn, especially pre-processing and pipelines, the pandas getting started and missing data guides, the NumPy beginner's guide, and the Seaborn example datasets used here. That brings us to the end of Chapter 3 on the Python environment and data preparation.